Okay, great. We are very happy to have Olga Soloveva, sorry for the mispronunciation, from FIA's Goethe University on QGP dynamics at finite chemical potential. Please.
Okay, good afternoon, ladies and gentlemen. Today we will discuss QGP dynamics in equilibrium and a little bit of equilibrium at heavy ion collisions. And firstly, we will start with a general motivation. We want to explore the properties of strongly interacting matter at the phase diagram where the finite temperature is not zero and is not so high, and the chemical potential is higher than in case of large hadron collider, for example. The problem is that there is available information from experimental data at region where the chemical potential is small, but in this region where chemical potential is not zero, there is not so much experimental data as well as not so much theoretical predictions from the first principles. Because in this region, complete constant is very large and usual perturbative calculations doesn't work. So we need to use another approaches, non-perturbative and also models to study this region. And in order to consider and explore experimental data, which will arrive soon at this region, we need to have some approaches and the model which needed for heavy ion collision simulations. For example, it can be transport models as well as some hybrid models where hydrodynamics and then transport is using. So, but the problem is that from the first principles, as I said, it is hard to obtain any predictions in this region. In recent years, lattice QCD techniques was established, but the problem is that at zero chemical potential, it works very well, but at small chemical potential, the lattice QCD calculations doesn't work. So there is also some methods and technique how to provide calculations at non-zero chemical potential, but for now, in the region where can be a critical endpoint, there is no data from lattice. And actually, what lattice QCD calculations can provide, it's mostly equation of state, which is microscopic description of the matter, while for heavy ion collision simulations, we needed microscopic properties, such as cross-sections or effective masses and potentials, which is essentially needed for the understanding what is going on. Here is one theoretical sketch how can the phase diagram of QCD can look. In this region, this is QCD crossover, where the transition is very smooth, and somewhere here should be critical point. It can be also down here, where the smooth crossover will go for first order phase transition. And in this calculation, I will describe the properties of QGP only in the region of crossover. So in order to study properties of this matter created in heavy ion collision, quark-gluon plasma, we can quantify the properties using the description of transport coefficients, which, for example, can be considered in the hydrodynamics. For example, it can be also input for hydrodynamic simulations. Here, you can see the strength tensor, T mu, and the baryonic current, and with dissipative parts. So these dissipative parts contain this transport coefficient, shear viscosity, bulk viscosity, and for example, diffusion. Here is baryon diffusion. It can be also charge diffusion or diffusion of strange quark, of strangeness. So, for example, if we consider shear viscosity, which shows resistance to shear strain, or in other words, it's resistance to the deformation of shape, while in simply case, you can consider that is the shape deformation while the volume is constant. But for example, bulk viscosity is related to the fluid expansion rate, and this is bulk viscosity shows resistance to the expansion. So these transport coefficients can quantify the properties of liquids, and it was very surprised where the shear viscosity to entropy density was found very small for QGP, because when matter is weakly interacting, then the shear viscosity to entropy density is high. For example, for meson gas, it is somewhere here. And in case of strongly interacting matter, the shear viscosity to entropy density is very low. And it was a big surprise that the shear viscosity to entropy density was found for QGP lower than for helium, for example. Here you can see this blue dots corresponds to the superconducting helium, or here, for example, for a water. As you can see, all these liquids has a minimum near the phase transition. Here is T minus Tc divided by Tc, and which tells us that actually these transport coefficients can be useful for a study of phase transitions. But the problem is that the shear viscosity tells us something about interaction inside the medium, which should consider microscopic properties, which we cannot find easily. So from the first principles, you cannot easily calculate the shear viscosity. In order to estimate the shear viscosity to entropy density or other transport coefficients, people usually are using models. And for example, the problem is that many models can have similar equation of state, for example, similar entropy density, but the shear viscosity differs very much for different model. So here, for example, model predictions for NGL and for our model DQPM, and in the region after phase transition, the temperature dependence of shear viscosity is very different for these two models. And it is only for mu equals 0. For non-zero, maybe the difference are larger. So there is a lot of techniques to determine transport coefficients.
Sorry, may I ask what DQPM stands for? You could.
Yeah, we will discuss it later, is Dynamical QuasiParticle Model.
Okay, thanks.
So, and here's few data for lattice QCD, but it's a bit old data, but just for some picture how it looks. And there are few methods which you can use in order to calculate the transport coefficients. One of the most common is Kubo formalism, when you are using correlation functions of stress energy tensor and then spectral functions. For example, it can be used as in a usual transport approaches, as well as in lattice QCD and ineffective models like NGL model and our dynamical quasi-particle model. Here, for example, some links for NGL model. You can see their calculations from for shear and bulk viscosity. And another approach is kinetic theory. For example, we will use later relaxation time approximation when we first calculate the relaxation time. So all the transport coefficient, as we will see later, is depending on the relaxation time. And the key quantity in order to estimate the transport coefficients are relaxation times. So the difference between these two approaches is that here we use already some approximation, and usually relaxation time approximation is needed less time to calculate on computer, for example, while for green Kubo calculations you need to have more. For example, for transport code you need to have a good statistics for your correlator, as well as for lattice QCD. It's a bit other problem that in lattice QCD they are determining firstly the correlator, and then they invert this correlator to a spectral function. So, but there is also another approach from kinetic theory. It is Chapman and Skog expansion, where you will expand your distribution functions in terms of Knudsen number, where Knudsen number is constructed as a ratios of characteristic microscopic and macroscopic length scale. For example, macroscopic is related to the gradients in the system, and the microscopic is often taken to be the mean free path of the particle. So usually Knudsen numbers are small. And another very charming new technique is holographic models, ADS, which is using ADS safety correspondence, where you can calculate observables in general relativity and in anti-de Sitter space, and then using the duality, you can relate it to quantum field theory. So here is some links for Son and Starnes calculations for example, for heat conductivity, and also calculations of Maximilian for bulk viscosity. And for example, in case of effective model, these different methods can give a little bit different values. For example, in our case, in DQPM, you can see here the green line is a Kubo approach, and the red line is relaxation time approximation. In ideal case, it should be the same, but in case of model, you cannot easily estimate the error. So we can say, for example, that if these two approaches are differs in 20%, it shows us the theoretical, so-called theoretical error, which our model are given. So firstly, let's consider QGP in equilibrium, and we will discuss dynamical quasi-particle model, which we are using. This model accounts for non-perturbative nature of QGP in terms of interacting quasi-particles with Lorentzian spectral functions, where you can construct your propagator and self-energy using the thermal masses and interaction widths. What we actually are doing, we are extracting coupling constant or thermal masses using the lattice QCD equation of state. And when we have the thermal masses, we will have the spectral function, which will give us our equation of state and all other characteristics. So this model differs from other quasi-particle model because we have an imaginary part of self-energy, where the gamma is the interaction width of a partons, which accounts for interaction with medium. So, as I told you before, firstly, we determine the complete constant. This is g squared. You can see here that it is a mass squared of quark, for example, and it depends on the temperature, chemical potential, and on the coupling constant. This formula is hard thermal loop calculations, but what we didn't put g squared because we don't know it. And in order to obtain it, we can use the formula for entropy density. In order to fix our entropy density to lattice QCD, we can determine g squared. So as you can see, here is only one parameter, it's coupling constant, which you can determine from lattice QCD equation of state. On the right, you can see the plots for masses of quarks. As you can see, it's increasing with temperature, but decreasing in µb. And here is the width. It is there is a very smooth dependence on µb. But as you can see, our gluons are heavier and has the same dependence in µb. So for quasi-particles, you can derive the entropy density and the baryon density using propagators and self-energy, which you can express in terms of mass and gluons. And it has been done by Boehm and Blazon. And what we are doing, we are using this formula in order to fix our coupling constant, g squared, using such fitting function. And when we fit our entropy density to lattice entropy density, we fix the model parameters. As you can see, we fix our parameter for µb equals 0 using the entropy density. This is the points correspond to lattice equation of state from Wuppertal-Budapest collaboration. And the lines are our output. The red line is just fitting. So And these lines, blue, orange, and pink, correspond to output from our calculations. So, and using this fixing, we can obtain the coupling constant. As you can see on the plot here, it is coupling constant as a function of scale temperature, T divided Tc for different μb. And as you can see, this coupling constant is decreasing with chemical potential. The trick which we are using for non-zero chemical potential, we are determining our coupling constant using the scaling hypothesis. As you can see earlier, all our MB dependence is here in this dependence mainly. So the scaling hypothesis tells us what if we consider g squared at non-zero MB as g squared for MB equals 0, where instead of temperature, we will use the effective temperature. So, and then what we needed is just the lattice equation of states, the lattice entropy density at μb equals 0, and then we will go further in μb without input from lattice. So here, for example, the formula for entropy density and baryon here for quark density in QuasiParticle model, where it is constructed with self-energy and propagators, which can be easily formulated on the basis of the masses and the widths, as it's shown before. Here is a Gluon propagator, and the self-energy is just the masses and the widths. So we fix our parameters at μb equals 0, and then we can have output at any μb non-equal 0. So for example, here for comparison, we show equation of state from DQPM. It corresponds these lines, and the points correspond to the latest data. As you can see, we fix here our model, and here we can reproduce lattice calculation. So this tells us that our scaling hypothesis works sufficiently well, surprisingly, actually. So, and just to sum up what we have done.
One question.
Yeah.
So you assume, of course, which is a reasonable assumption, crossover at this μb equals 0.4. Is this correct?
Yeah, this is correct. Here we will discuss only the crossover region. Now I'm working on the expanding this model in higher MB and the first order phase transition, but for now we will consider only crossover region. Yes.
Okay, thank you.
So the key ingredients for quasi-particles is masses, widths, and couplings, which can be fixed using lattice entropy density. And when we fixed our parameters, masses, widths, and coupling constant, we can extract spectral functions. And using spectral function, we can calculate the thermodynamic quantities such as entropy density and quark or baryon density, which later you can use for extraction of pressure and energy density. So here you can see our comparison with lattice, as I showed you before. So now when our parameters are fixed, we can calculate more interesting quantities. But our goal actually is the transport coefficients. So just small reminder about transport coefficients in relaxation time approximation. We will use relativistic Boltzmann equation for quasi-particles, where for this approximation you can express your distribution functions a little bit of consider a little bit of equilibrium. So here is equilibrium distribution functions, and here is a small correction. So, and in relaxation time approximation, you can express the collision terms as f minus f equilibrium minus f divided by relaxation time. So as you can see this equation, so you can express the difference in df as f equilibrium minus f, which transforms in this form, where tau is relaxation time, which express the time while system reach equilibrium again. So in general, relaxation time can be expressed using transition rate here. Actually, we are using this formula for relaxation time, which in general depends on the energy or momentum. But you can also simplify this this formulation of relaxation time. So the trick is that you can express the stress tensor and the current in terms of distribution function. And using the conservation law, you can express the transport coefficient, shear bulk viscosity, or diffusion coefficient in terms of your distribution function and relaxation time. So that is the main trick. And but your results are strongly depending on the relaxation time. So as I said, this is the general form, which is the best for usage, but you can simplify it as it done in many models. In case of dynamical quasi-particle model, you can calculate the matrix element and then the cross sections and interaction rates, which is 1/t. So relaxation time can be calculated using interaction rate, or if you have the quasi-particles with a finite width, the width actually tells you the interaction rate. So in our model, our width from spectral function is related to the interaction rate. So it's we will consider two cases. First, it's more general and accurate case. It will correspond red lines, and more simplified version where there is no energy dependence will correspond to the green dashed line. So here I'm showing you the relaxation time, which we're calculating using this formula, but it was averaged over momentum. And it's an interesting question, actually, which degrees of freedom are more relevant for transport coefficient. And as you can see, that for more heavier degrees of freedom, the relaxation time, and also for more strongly interacting degrees of freedom, the relaxation time is smaller. So for gluons, relaxation times is around twice smaller than for quarks. And another fact that you can see here a very smooth dependence on μb. Here, the relaxation time in Fermi over C as a function of μb and scale temperature. And from these graphs, you can already expect that there will be not strong maybe dependence for transport coefficients. So in order to calculate the relaxation time or interaction rate, you need to calculate the matrix element. So we have considered leading order in DQPM, but our model accounts for resummed propagator. So we have considered the PQCD matrix element where we have non-zero masses. So it is like screening the biomasses, and we have considered addressed propagators. So here you can see the diagrams for quark scattering, gluon quark, and gluon scattering, which we're taking into account. And using these matrix elements, we have calculated the cross sections as a function of temperature and maybe. And here I will show you also the cross sections, the total cross sections as a function of square root of S. And as you can see, it is decreasing with temperature as well as with baryon density. Here is the UU cross section. But as you can see, the decreasing in temperature is more sufficient than dependence on maybe. And for quasi-particle model with finite widths, you can consider a few cases. We will consider for transport coefficients here on-shell case, where we fix our masses as the pole masses of our spectrum function. But in principle, for other quantity, not for Boltzmann equation, but for other equation, you can use off-shell definition. For example, in our transport code, where the initial masses are taken as a pole masses, but the final masses are integrated over spectral function. So, but actually the difference here is not so big. You can see the dashed line is on shell and the solid line are off shell sections. So we have seen that here the total cross-section actually is decreasing with temperature and decreasing with maybe. And using the cross-section, we can evaluate the relaxation time, which is key ingredient for transport coefficient. So let's start with shear viscosity, where we are taking into account quarks, antiquarks, and gluon as well. So you can see here the formula from relaxation time approximation. And on the plot, I show you the different contribution for this relaxation time. Here, all the shear viscosity are divided by the same value because it's not eta over S, it's not additive quantity. So here I show you different shear viscosity divided by the same total entropy density, which corresponds to which coincide with the lattice ones. So as you can see earlier, the main contribution actually comes from the light quark. This is the orange line. So we are expecting it because our relaxation time for quarks was twice and more larger than for gluons. But as you can see here is the energy squared. So actually the mass of the particles are also playing a role in the contributions to the transport coefficient. So you can see that in case of gluon, which have larger effective mass, the contribution is around 10%. Here, I plotted the result for total shear viscosity as a red line, in case of momentum-dependent relaxation time. And the dashed green line corresponds to the case where there is momentum dependent is not using. So here the relaxation time depends only on temperature and maybe. And as you can see, this value are actually very close to each other. So the main contribution of energy or P dependence to the transport coefficients are in the phase transition region. So the data, the points corresponds to the lattice viscosity data, but unfortunately for Gluon dynamics, that's why we actually cannot really compare our result to lattice QCD, especially near the TC, because for Gluon dynamics, here is a phase order phase transition, while here we have a smooth crossover. So, but we are more interesting in the MIB dependence. As you can see, the dependence of shear viscosity is quite smooth, as we expected from the relaxation time. And you can see here it's slightly increasing with MIB. So, but unfortunately, from this point of view, you can feel that maybe in heavy ion collision, we also didn't expect to see any MIB dependence if we will have such smooth dependence on relaxation time on MIB. So another interesting transport coefficient is bulk viscosity, which we have calculated using the same technique. Here is the relaxation time, and here's the speed of sound. This is the energy, and here is actually second derivative of our effective masses, which we obtained using our model. So as you can see, near the phase transition, actually shear bulk viscosity over entropy density is not zero. It's decreasing in temperature, and it's very small, already around 2 TC. But in the vicinity of phase transition, it is not small. You can see that actually our data are very close to lattice estimations, and you can see here, for example, estimation from holographic model of Maximilian for few cases. But the main point here is that the maximum value of bulk viscosity over entropy density is around phase transition, and it can play sufficient role for transport and for hydro calculation. We also have considered the MIB dependence of this transport coefficient, and as you can see, it has also very smooth MIB dependence. So in using the same technique, you can obtain also the electric charge diffusion coefficients or electric conductivity. So here you can see our results in red and green in comparison with lattice calculation and with hadron resonance gas calculation of our colleague Jan Fatakis. And in case of conductivity and baryon diffusion coefficient, you take into account only quarks. So here, for example, gluons are taken into account only in relaxation time. So for the baryon, for the MIB dependence, it has the same trend. It is increasing with MIB, but for baryon diffusion coefficient, the trend is different, because here you can see that the increasing of baryon density will increase the baryon diffusion coefficients. And here you can see a comparison with hadron resonance gas data and some Champanek-Skoll calculation for PQCD cross-sections. And also, it was interesting to compare with a formula obtained by ADS-CFT correspondence. But here we have used the formula from Son and Starnets and put our equation of state. And as you can see, that our values are higher as in case of shear viscosity than ADS-CFT correspondence. So in order to consider out of equilibrium situation, we will study the simulation of heavy ion collision. So interesting point that you can study heavy ion collision using different methods. For example, here I depicted some hydro model. So it starts not from the beginning, but from some initial early stage when it is needed some initial initial input for hydro calculation, and then it describe evolution of quark gluon plasma, and then, for example, you can use some afterburner, which will come to the final stage, and you can extract observables which you can measure on experiment. And another very simple model is thermal models, when you can extract the temperature and baryon chemical potential using the number of particle or distribution in rapidity. So it's a very useful model in order to understand the values of temperature and maybe in heavy ion collision. So, but very useful models is this transport simulation, which starts from the initial part and goes to the final part. So we will discuss today results from Parton hadron string dynamic code. This is the transport theory, which based on the phase space representation of Kodanov-Bain equation, where the partonic and hadronic phase are implemented and the propagation are explained in the same techniques. So here you can see, for example, schematic picture of gold-gold collision for central collision. B is impact parameter equal to Fermi. Here you can see the formation of quark gluon plasma phase. This corresponds to the red and green points. And after some expansion, you can see that here actually there is not so much quarks and gluons, but there is more mesons. And here you can see some baryons and antibaryons. But later on, it is mainly only the mesons here. So shortly, brief overview of PHST. So it starts from the initial nucleon-nucleon collision, where the Lund string model are used for string formation, and then the string decays to the prehadrons, baryons, and mesons, and then for partonic phase is occurred when this conditional energy density is larger than critical energy density, which is around 0.5, 1 divided by Fermi cube. So the partonic phase is described using dynamical QuasiParticle model with massive quarks and gluons. using elastic cross-section, which we have discussed a bit earlier. And later on, the hadronization occurs using the formation of off-shell mesons and baryons. For example, we will form the raw meson, which will then decay into a pion. And it allows us to momentum conservation and conservation of quantum numbers. So, and the hadronic propagation is described by hadron string interaction. It's a well-known version of PHSD's HSD code. So later, we will consider a few versions of PHSD. Before, in PHSD, we will have taken into account only the temperature dependence of the cross-section, and actually cross-section wasn't estimated using the matrix element. It was some temperature and energy dependence, energy density dependence of cross-sections, while now it is calculated using the matrix element and the estimation of temperature and maybe. The key point here that now, in order to see some temperature and maybe dependence on the observables, we need to implement the extracting of temperature and maybe in the code. So we are extracting temperature and maybe using the energy momentum tensor. In each, we have calculating in each space-time cell the energy momentum tensor. Then we perform diagonalization in order to obtain energy density and the pressure in the local rest frame, which will tell us the energy density and the baryon density, which we can compare with our DQPM results or lattice QCD results. So we can extract in each space-time cell the baryon density and the energy density in PHSD, and then using the coefficients from lattice QCD in expansion of μb over t, we can extract μb over t using this system of equation. So, as I said, firstly, we estimate the energy density, and then we extract the temperature and maybe in each space-time cell. Here, for example, the energy density is depicted in for different cells as GV over Fermi in cube. So for time, 2.6 Fermi over C. So now we will focus on the temperature profile in X and Y and mid-rapidity at the time 1 Fermi over C and 4 Fermi over C after the initial collision in case, and also here is the profile in chemical potential. So as you can see, these distributions corresponds to the transverse plane orthogonal to the beam direction at mid-rapidity. So, or in center of collision zone. And for early times, we find that the temperature of the fireball are well above TC. You can see it by the color. So it is around 2.50 GV. While for temperature equal 4, it drops down already to average value 0.18 in the center of zone. And you can see that fireball expands and cools down very fast, while for baryon chemical potential, you can see that initial baryon chemical potential is quite large, but it also drops very fast to the value 0.25 GeV. So, which is in accordance to some thermal expectation from thermal models. So, if we consider evolution of the distribution in temperature and maybe for different time, you can see here the distributions for QGP cells at mid-rapidity in case of light-light collision. On the phase diagram, we are considering here the crossover. Sorry, here is the MB. So this is the maximum value is 0.6. Here is 0 MB. And at early times, the maximum is around 0. The MB can reach 0.6 GeV, while already for times in interval from 2 to 4 Fermi LC, the maximum has dropped already to an average temperature 0.18 GeV, so it's somewhere here. And the average baryon chemical potential is 0.25. So this value are in accordance with expectation from statistical model. It's interesting to see how the evolution of fireball in case of temperature and maybe with time, because one can expect very high temperature, for example, for this collision, but actually, as you can see, the fireball expands and cools down very fast. So here already it's this time t larger than 4 Fermi over C, the QGP cells are mostly near the crossover line. But the goal is to find the traces on the observables at the finite MB. So we will consider a few setups for PHSD. PHSD4 corresponds to the cases where the cross-sections and effective masses of quarks and gluons depends only on temperature. It will be green line. The blue line corresponds to the PHSD5, where we have angular dependence, or here I put square root of S dependence, and temperature dependence, but MB is equal 0 everywhere. And PHSD5, our red lines, corresponds to cases where we consider cross-sections depending on angular dependence, temperature dependence, and MB dependence, as well as effective masses also have temperature and MB dependence. So here I show you the results for gold-gold collision at energy 200 GeV. And here is a rapidity distribution in comparison with the experimental data. What you can see here that actually all three lines are very close to each other, and only the angular dependence can be seen at the mid-rapidity region. So here depicted the PT spectra of the particles. This is pions, kaons, and protons, and the result is the same. Actually, all the lines are quite close to each other. But maybe we are expecting to see some maybe dependence at small square root of s energy, where the higher maybe value can be obtained. But unfortunately, if we lower the collision energy, also the fraction of QGP is smaller. So here you can see only difference between the versions without angular dependence of cross-section and with angular dependence on cross-sections. But you cannot see the difference for versions which are taking into account the MIB dependence. So in order to study more sensitive observable to the QGP, we will study anisotropic flow coefficient. To quantify transverse momentum as anisotropy, one can expand the azimuthal distribution as a Fourier series, where the flow coefficients Vn is the order, the magnitude of n order anisotropy, and here is psi corresponds to the event plane angle, which characterize the initial collision geometry. Here, for example, you can see the collision of two nucleons, which are creating the fireball in the center, and the shape of this fireball can be related to this anisotropic coefficient. For example, in case when V2, so second flow coefficient, or elliptic flow is non-zero, it will correspond to the elliptic or almond shape, and depending on the sign of V2, it can be in this direction or in this direction. So we will consider mostly directed flow, the V1 coefficients, and elliptic flow V2 coefficient. The advantage of transfer code is then you can trace back the history of the particle, and we can extract from which channel these particles are comes to the final stage. And here I showed you the flow coefficient depending on pseudo-rapidity for different versions of PHSD 4, 5. And you can see it is the same observation, that here only dependence on angular distributions shows up, and you cannot see actually the MIB dependence. And the interesting things which one can consider is actually which contribution of particle which come from QGP phase and how their scattering are affecting the values of B2. And here you can see, for example, the flow coefficient for different particles came from QGP or decay or string without rescattering in our model. And the value corresponds to the contributions. So the main contributions come from the particles, which comes from some decays. And particles which have a lot of rescattering are actually don't have so much information about the QGP. And here, for example, you can see that actually around 30% of the contributions came from particles which came directly from QGP, from hadronization without rescattering. So, and you can see here it's without this weighting, it's just the V2 of different particles came from different channels that, of course, V2 of particles which occurs directly from QGP without scattering is actually larger than flow coefficients from particles which came after rescattering, after some decays. But unfortunately, because the fraction of QGP, because there is a lot of rescattering, you cannot see the effect of these particles. So the final contribution is really small to show some maybe dependence. And we have studied as well V2 for baryons and antibaryons for different energies, because it's more interesting to study small energies where maybe dependence is lower. But unfortunately, in these cases, the maybe where square root of S, for example, is 27 GeV, maybe it will be larger, but the fraction of QGP is too small to see any difference in the observable. So I want to sum up that we have discussed transport dynamics of QGP in and out equilibrium, which have been described using dynamical quasi-particle model in equilibrium. And we have considered also out of equilibrium study of QGP and searching for any maybe dependence in observables. But unfortunately, we didn't see maybe dependence in observables, because at high maybe regions which are probed at low square root of QGP fractions is small. And the effect of maybe is cannot seen, while at high energies, the maybe is very small. So our conclusion is that it's very hard to see on observables the effects or the characteristics of QGP phase. And we are expanding our model at higher maybe in order to study more observables, and in order to see where the critical endpoint will show up. So thank you for your attention.